So this video is going to discuss the 1769 IF4X0F2 analog input, analog output card for the CompactLogix chassis. So this is for the chassis 1769, hence the first four numbers in the model number. And then the rest of the model number is IF4, so that's 4 inputs and 2 outputs, OF2. And this is a low resolution card. It's only 8-bit, all right? And so 2 to the 8th is 256 values, with one of those values being 0. And so therefore the maximum value would be, at least theoretically, 255. However, what the Allen Bradley does in the RSLogix software is when it reads in data from an analog input, it reads it and as a 255 analog to digital conversion, but they shift that conversion over 7 bits to the left. And so what happens is, here's like your 8 bits, and of course 8 bits, they get shifted over 7 more bits, and so you actually end up with a 15-bit number. Okay, so this data is stored inside of an integer, which is a 16-bit signed tag value inside of the RSLogix software. All right, so we actually have a total of 16 bits, but the leftmost bit is S, and of course it would actually be 0 because it's a positive number. This card only reads in positive values, and so it's reading in, so it'd actually be, all zeros here. I just put the S there to indicate that it's a signed bit, okay, but that signed bit would be a 0. Because they're going to be positive numbers. Now, your highest number would be 8 ones, right? So when the analog to digital converter reached the maximum it could, it would make the value all ones. Then there's 8 ones. So that gives you 8 ones shifted over 7 places. So the maximum value that this card can actually read would be 32,640. Okay. Right. This is a picture of the input card wiring terminals here. Okay. And if we look right here, so here's our CompactLogix. This is an L23E, so it's got 16 bits of digital DC input, 16 bits of DC digital output, and then we have a relay module added on, and then this is our analog card. So you can see it actually shows you the wiring right here, and I just have them on the screen. Sorry, I switched back and all right, so I just have them on the screen here to make it a little bit easier to read in the video. So you can see we have channel 0 and channel 1. There's 4 inputs. Okay, so they count from 0 to 1, 2, 3, and then the output are down here. So to set this up, you can read current signals, which are going to be anywhere from 0 to 20 milliamps, and technically it can go all the way up to 21 milliamps. I'll look at that in a minute. And the voltage, okay, the voltage in would be from 0 to 10 volts. Okay. All right, so this is actually the manual for the Allen Bradley here, and just right here it kind of shows the wiring. The way this is wired is you have either current in that's going to go through this resistor right here where the mouse pointer is currently at, and so this is a 250 ohm resistor. Current's going to be reading is going to read in through here, and then back out the minus sign down here. So it comes in, IN, this is an I, capital I there, IN plus, that's current's going to come in, and then it's going to go out the bottom if you're feeding it in a current. If you're going to feed it in a voltage, then you would wire it to this terminal here, and it would go through both resistors, where this upper resistor is a much larger resistor. And then there's a multiplexer circuit in here that comes over and then feeds that signal to the analog to digital converter, comparing it to a reference voltage. And then that reference voltage then is going to be used by the analog to digital converter to determine the actual value, and then of course it converts that into a binary, into the number, into the integer value, and stores it in that 16-bit location. Okay, so that's what the wiring looks like actually inside of the card. All right, so to use this card, one of the first things that we could do is use the RSLogix software to view the PLC and see what is connected, see what modules are plugged into the PLC. So you can see here, this is our PLC, the 1769 L23E on the 158 IP address here, 10.101.201.158, and the you can see in the slot 4 for the module is actually listed as unrecognized, which is not too helpful. Normally you can look, as you can see here, you can see the two embedded, you can see the 16-bit digital input and the digital output, and the 16-bit relay modules. Those all show up so we can see what those are, but for some reason this version of RSLogix is not recognizing this low resolution card. All right, but you can see on the door, if you look down here, we can see the number of the card. You can always look on the door of the card and they'll show you the model number there. Okay, so then what we want to do is go to RSLogix. Okay, so we're going to open up RSLogix here, and I'm going to just create a new program. Okay, and my controller is the 1769 L23E QB1, and then we have to select the revision or the firmware version. This is firmware version 20 on this PLC. And what I'm going to do is I'm just going to set up a current analog to digital converter value here. So I just want to be able to, actually I'm going to do digital to analog to analog in. So what I'm going to do is I'm going to feed it out. Let me show you the diagram here. Okay, so what I want to do is I want to just kind of test this and see what's happening here. So I'm going to take the output, which we have our terminal block. So I out of channel 0 is coming out of the terminal block pin 22, and then that's going to go into pin 17 of the terminal block. But what I'm going to do is I'm going to hook up a meter there. So now the positive is going to go, the positive of the meter goes to the output because current's coming out the output into the input. So as far as the meter is concerned, the negative of the meter would go to the connection of the input. And then where the current comes in, and it's going to come out pin 16 of our terminal block, which is the V/IO minus, and it's going to come out and return to the analog common for the output module. So we have our digital to output module, And then we have the analog to digital module. So this is the wiring that I'm going to do. So let me show you here with the camera. So with the camera here, I have my terminal block. So here's the terminal block. There's actually 25 terminals on here. And all the analog ones are in this last section here, so 15 through 25, okay? And so the current is going to come out 22 here, so it's going to come out 22, and I'm wired then into a meter, so I have a digital multimeter up here. Okay, it's just reading microamps at the moment because I don't have a program sending anything out, so it's basically zero. So it's sending out essentially zero current, 55 microamps is what the meter's actually reading. All right, but we're going to come, current is coming in the positive of the meter, okay, into the positive of the meter, out of the meter, into our input of our PLC, which actually should be pin 17. So I've got this currently wired into 16, which is incorrect. So I need to actually take this and run this into 17 here. Okay, so again, so current is coming out of pin 22, which is wired to our digital out I positive, into our positive of our current meter, out of the current meter, into pin 17 of the terminal block, which is I positive of channel 0 input, and then we're going to come out of 16 and back into the ground. Okay, so 16 is the V/I 0 minus. Okay, so we're now, remember it's current, so we need a complete circuit. So this this black wire is completing the circuit from the output of the analog to digital input card, returning back to the output of our or to the ground of our output card to complete the circuit. All right, so that is the wiring that we're going to do. Now, before we get into that, I just wanted to point out here that, as I mentioned before, the analog card can actually do 21 milliamps out. Okay, so it can actually do 21 milliamps out, and the input cards can handle 21 milliamps in, which is the the maximum number for that there is at 32,640. All right, so if you wanted 20 milliamps, right, then you're taking like that max number times 20 divided by 21 to get the ratio. So your maximum value is going to be about 31,086. Okay, so for 20 milliamps exactly, we should have a value of about 3186 milliamps. If we wanted just simply 4 milliamps, we would end up having to set a value of about 62,017. All right, but since we're shifted, let me return to this slide for a minute. If we're shifted, since we are shifting 7 bits, these 7 bits are just always 0, and so to get a 1 out, okay, that would give us about a value. That would give us a value of 128. Okay, so if we wanted a 1 on, say, our digital to analog out, okay, we would actually have to put in a value of 128. So if you put in a value of, say, 3 or 7 or 18, that's actually still just going to be a 0. Okay, so the output won't change until you change your value by a value of 128, because these first 7 bits here are ignored. Okay, so we'll see that when we build the program. So let's go ahead and flip over to our RSLogix here. All right, so this is just the name of my program, and I am going to store this on my D drive here. Okay, so I just put in D:\/ to store this. Okay, and I say OK, and it's going to generate the program. Or generate the basic core files needed for our program, at least. Now this may take several minutes here, so we just kind of have to wait till it runs. I actually paused the video there for a little bit just to give it a chance. So now you see that it has come up here. Now again, this is the L23E, so it has these 2 embedded modules for digital in and digital out. And so it obviously recognizes those. Now, but what we have to do is we have to come down here to our expansion I/O, because we have our 2 modules there. So we right-click, say New Module. All right. Now, the first module connected is the OW16. So knowing that, up here in the search window, I can just type in OW, and you see that brings down all the choices down to a simple 5, and we can just select it. Or if you wanted to, you could actually just type OW16, and that would be then your only choice. Okay, but you can, just OW would be enough to get it. So I'm going to create that. Now this is a relay module. So when this module pops up, I'm just going to come in here and I'm just going to name it relay, because that's my relay module. It's in slot 3. Okay, if you add them in order, it'll automatically make sure the slot number is correct, and you can add a description here if you want. There's not really any configuration you need to do with this unless you wanted to like set up faults or anything. We're not going to cover that in this video. This video is really addressing the analog card. Now, one thing you could do is you could set the revision of your card. Actually, with this CompactLogix, it's not too picky about that, so we could not mess with it. But if you see, it's defaulting to revision 1.001. Okay, so that's the revision number. And so if we wanted to set this correctly, we could click on change, and we can change that revision number. Now the question becomes, well, what's our revision number? Well, if we flip over to RSLinks and we go to our relay card and we right click on there and say device properties, it tells you that it's revision 3, major revision 3, minor revision 1. All right, so that's how we can tell that, at least if it's recognized, which the OW16 model is. And so we can actually see that this is actually revision 3, and we can set that. For this class, we can actually do away with that, and it'll work okay. I've never seen any issues. But when you get into some of the advanced features with faults and stuff, it becomes important to make sure that you have the correct revision set. All right, so now that we've set that, I want to do my analog. And this is a low resolution, so if I just type in low, it's the only choice that comes up. So this is my card. Again, it's the 1769 IF4X 0F2. 4 channel inputs, 2 channel outputs, but and low resolution analog card. All right, and so that's the quick way to get that. I'm going to create this. It automatically puts it in the next slot. So again, you want to put these in order, and so your slot will always be correct. This is an analog card. I'll just call it analog. Now, we do, if we're going to use an input, we have to come into input configuration, and the only thing we have to do there is say, basically, turn it on. Okay, that's our only choice with this particular card. Other analog cards have a lot more choices sometimes, but this one here, all you got to do is say, yes, I'm going to be using this input. And likewise, if you want to use an output, you have to come in here and enable it. Okay, so they're disabled by default, so if you don't enable them, it's not going to work. Okay, you know, it probably doesn't really hurt too much to enable the other ones, but if you're not using them, you should just leave them disabled. All right, so we've added all the modules that we have connected here, so I'm going to close that. I'm going to come over to my main program, and I'm going to go to Program Tags, and I just want to create just a few tags for right now. All right, so the first tag that I want to create is going to be my input channel 0. Okay, and so that is going to be a local module. It's module 4, and this is an input, so I for input, and then channel 0 data. Now I just typed that in there. But if you can't remember what it is, you can click the drop down and you can select it. Okay, but the nice thing about this is if you want to add more, once you've got it, you can copy it. Now I'm going to do an output channel 0. Okay, and the only thing that changes here is the I changes to an O, so I can just copy and paste it and select it very quickly and easily. Okay. All right, so now we're going to be bringing in values. Okay, so we're going to be bringing in value based on our output value. And so to do this, we need a value out. So I'm just going to call force output. Okay, and this is going to be an integer value, which it defaults. There's no alias because all I want to do, I just want to come in here and be able to type this value in. So this is just a tag that I can type in the number at any time. And so what I'm going to do is I'm just going to start here for this value, and I'm going to set the value to the 32,640, which is the maximum, which should actually be 21 milliamps. Okay. And then I also want to read the input as milliamps. Okay, so I'm going to say n comma milliamps, and this is going to be a real value, so I'll use a compute statement to convert that. Okay. All right, so one other thing that I'm just going to do here is I'm going to create a tag called 8-bit, and we'll just use a compute statement to view that. So what I want to do is we're going to look at our forced output, which is our 16-bit, and then I'm going to use that 8-bit. We'll use a compute statement to just shift that back 7 bits to the right, okay, and then we can just see that as an 8-bit value as the card is actually reading. All right, so doing that, we're going to come over here. We're just going to create our tags. So what we need is a move. So we want to move our forced value, and we're going to move that to our output. Okay, so this is just going to allow us to force that output. Okay, and then we're going to, I want to just move or not move, it's going to be a compute. Okay, so I want to compute, so I'm going to compute the 8-bit value is going to be my force output, okay, divided by 128, which is 7 bits. Okay, so I'm going to divide it by 128, so I just want to view that value. And then I'm going to have another compute statement, which is going to be my scaled value. So my destination, right, is going to be my in milliamps. All right, and then we just have to scale that. So the input, how did I name the input here? So the input is input underscore channel 0. Okay, so this is just going to be input channel 0. All right, so input channel 0 times 21 milliamps divided by 32,640. So remember, the card can read all the way up to 21 milliamps, and when it does that, it'll be reading 32,640. So this is basically 1. We're multiplying the input times 1, but what we're doing is changing the units. So 21 is 21 milliamps. And then 32,640 is the integer value that 21 milliamps would turn into. So that's going to be our computational state. And you could actually just do the math and multiply it times whatever that comes up to. Or just leave it, do it right there, and that way it's easier to see what you're doing. And so what we're going to do then is we're going to move this into that tag in milliamps that I created. And so if we look at that, yeah, my in milliamps I created was a real, but I'm gonna make that an integer again for starters. So I'm gonna make this an integer, and then we'll see the difference between why it needs to be a real. It really does need to be a real, but I'm gonna just make it an integer first. So again, I'm going to come up here and I'm going to set my initial value to be 32,640. And I'm going to save this program. And I've already set my path. So now I'm just going to come here and download the program. All right, now I'll give you a little quick here. You notice here, it always pops up this and, asks you if you want to download. Well, it's defaulting to download, so you can just hit the space bar with your thumb, okay, instead of dragging the mouse all the way over to the download button and then pressing it. If you it's already selected, just either hit the enter key or the space bar and it'll apply. Then it's going to come up here and prompt us, do we want to go back to run mode? And it's defaulting to yes. So again, it doesn't matter where the mouse is at. If you just hit the space bar or the enter key, it'll execute that button. Or you can drag your mouse over there if you want to take your time and get the mouse over there and click that way. But so now it's in run mode. So now if we look here, you can see that we're forcing 32,640 out. Okay, and so if we look at the camera here, let me add the camera. All right, so you can see the camera is on the meter right now, and it's showing 21.0 something milliamps. Okay, so up here in our we're forcing out 32,640 to the output. So this is going to output, right, O channel 0. And then that's feeding it through the meter and then back into the input. And you can see here is our output. All right. So now if we flip back over to this slide for a minute, okay, so you can see here, like if we put in like some values, okay, so I had it like 4 milliamps would be about 6,200, okay. So if we come over here and we force in 6,200, okay, then we're at about 4 milliamps, okay. And so if we double that, right, so if we go to about 12.4, okay, we should be at 8 milliamps, okay. So what if we wanted, say, Okay, so basically 1 milliamp is a count difference of about 1500. It's actually 1554. All right, so if I wanted, say, half an amp, right, it would be about half of that. So let's say that if I put in 6217, that gives me about 4 milliamps. Let's say that I wanted 4.5 milliamps. Well, if I put in, about 700 and about, just under 800 there, above that, that'd give me about 6994. Okay, so 6994 should give me 4.5 milliamps, okay, or somewhere around there. So if you look at the meter, you can see that it's actually 4.57 milliamps is actually what the meter's reading, right? 4.57 milliamps. But if you look at the integer value here in milliamps, okay, it's just showing 4. It's not showing 4.5. And if I bump it up a little bit more, let's call it 7100, for instance. So if we go to 7100, okay, our current didn't even seem to change there. Okay, 7400. Okay, so if we change it to 7400, we're at 4.8 milliamps. Okay, and the reason it didn't change is, remember, this is only an 8-bit card, and so you have to kind of increase it. I didn't go through the calculations here on the resolution change, but increasing it just a couple of hundred wasn't really enough to get it to change the output of the card. But so right now the output of the card is reading 4.8 milliamps, but this is just still saying 4, not 8. This is saying 4 milliamps because it's an integer. Okay, so if we come up back to tags, well, I got to go offline, okay, and I'm going to change this. This here needs to be a real, okay? This needs to be a real. This in milliamps needs to be real. So the only thing I'm changing here is I'm making this real, and I forget what value I had in there. 70. Let's see. Let me download this. Okay. Say yes, okay, and come back here. Now, since I downloaded it, reverted back to my default value. So I'm going to go to 7200, all right, and you can see that 7200 is actually giving me 4.65 on the meter, and it's reading just slightly different right here. It's 4.69, okay, so a little bit of difference there, but you can see 4.69. But notice what's happening, if we watch it here, it's toggling between 4.69 and 4.61. Okay, and so what's happening is the true value is in between there, but because we only have a 8-bit resolution card, it can't quite get that, and that's why it's like toggling back and forth here sometimes. It's toggling back between 4.61 and 4.69 because our resolution we're in between. We're actually getting 4.65, and we're actually kind of in between that in there. The true value is in between what our resolution can do. So that's why that's kind of toggling back. Okay, there also might be a little bit of noise in there, but if you look at, if you hover over the input channel it says 7269, and that's actually not moving at all. 7269. So the conversion seems to be bouncing back for some reason. But the input value is actually just, I haven't seen it actually move at all. But sometimes you'll see it move due to a little bit of noise in the system or something and just fluctuate a little bit. Okay, but that is the Allen Bradley CompactLogix 1769. Okay, I had the chassis is 1769 here, IF4XOF2.